How to draw a best fit line and name a correlation. In this class, we're going to name correlations in 3 ways. One of those is a positive correlation, the next one is a negative correlation, and the last one, we say there's no correlation. Each one of these has an example drawn beside it for you. So a positive correlation is when y tends to increase as x decreases. We use the word tends because every point doesn't necessarily follow this trend, but in general, we can see that as x increases, y does too. Take a second to look at this figure over here and see what it's actually telling you. So this point here, as x is increasing along the x-axis, we're going to say y is increasing too. So we go from this point that's circled now to this point here. So we're continuing on the increasing, the positive end of x, and we're also going up in the y direction, which is increasing in y. So we know that y tends to increase as x increases. For a negative correlation, which is this next one, it's the opposite. Y tends to decrease as x increases. So as x is increasing along the x-axis in the positive direction, our values of y are actually getting lower, so they're actually decreasing. So going from this first point I circled here, if you go in the positive x direction, so x increasing, and you end up going in the negative y direction, which means y is decreasing. And our last example is no correlation. This is when x and y have no apparent relationship. When we say there's no correlation, we can't draw a line of best fit that we feel accurately describes our data. All of these lines that we have drawn, so this one here and this one here, these are called lines of best fit, or best fit lines. We'll learn how to draw one of these ourselves soon. But this one, because there's no correlation, there is no line of best fit. And I'm going to call it line of best fit, LBF. Now that we know how to recognize a line of best fit, we're going to learn how to actually draw one on a set of our own data. So there are 4 steps you need to follow in order to do that. Our first step is to make a scatter plot. To make a scatter plot, you want to always draw your 2 axes. Sometimes you'll have just the quadrant number 1 where both values are positive, like this here, or other times you might have the full coordinate axis. So where these are all, this is the x and this is the y. So it just depends on the type of problem you have. So on your scatter plot, you always want to label this is x, this is y, and you also want to have a title of what the axis is, whether it's time or some sort of data, and what the y is, and you want to include units. So remember to include units here. So it'll be units, but it'll also be a description of what the axis is. So I'll call that axis name. Okay, so then what you'll do is you'll plot your data, and you'll plot them as a scatter plot. So a scatter plot means that you have individual points. So you get a bunch of points, and this one right here looks like a positive correlation because x is increasing as y increases. So now that you have your scatter plot, and you'll also want to make sure to write a title on that, you get to do step 2, which is deciding whether the data can be modeled with a line. What we're asking here is there a correlation? So remember, a correlation would be positive or a negative correlation, but you cannot draw or model the correlation with a line if there is no correlation. So is there a correlation? Is it positive or negative? If it's positive or negative, then you can model. So yes. If it's a no correlation, then you cannot model it with a line. Step number 3 says to draw a line that appears to fit the data closely. Approximately half the points should be above the line and half below. So with our example we have up here in the top right, we're going to go ahead and draw something that's going to look like a line of best fit. So it's going to go approximately through half the data. And we can even go through and actually count the points and see if that's correct. So we have 1, 2, 3, 4, 5, 6. And then we have 1, 2, 3, 4, 5, 6. And then these are pretty much, the ones that are right along here are pretty much on the line. So that's actually a pretty accurate line of best fit here. Now that we have a line, we can go to step 4, which is to write an equation using 2 points on the line. These don't actually have to be data pairs. So now that we've already have our line of best fit to model the data, to give an example of the data, we can actually just choose any 2 random points along the line. So this one right here, there is a point there already, so I might choose that one. And then I can just choose a random point on the line here where we didn't even have a data point that existed there, but it's on the line. So you use those 2 points and those 2 ordered pairs. We don't know what this data set is, so we don't know what they are right now, but you can use those 2 points to find the equation of a line just like you did in chapter 4. Let's go ahead and try an example. This one's on bird populations. The table shows the number of active red-cockaded woodpecker clusters in a part of the DeSoto National Forest in Mississippi. Write an equation that models the number of active clusters as a function of the number of years since 1990. If you refer back to your steps for solving one of these equations in the previous slide, you'll see that the first step is to draw a scatter plot. So in drawing a scatter plot, we only have positive data. So I'm going to go ahead and draw my axes. This is going to be the first quadrant, and you'll want to use, if you're not doing this on a screen like I am, you're going to want to make sure to use a ruler. So this one's going to be the x-axis. This is going to be the y-axis, and then you want to go ahead and label your axes. I've gone ahead and labeled the x-axis as years since 1990, and the y-axis is active clusters. Okay, now it's a little bit messy, but I went ahead and also labeled this axis. I'm going to go, every single one is going to be 1 year past 1990, so at 5 marks we have 5, and at 10 marks we have 10. So that's what I labeled there. On the y-axis, I did this little squiggly thing, which means that we're not going to start at 0. We're actually going to start somewhere else, and we're starting at 20. So you have to specify what you're starting at here on the first line. And then every single line is going to be 5. So this one, 2 lines makes 10, and then 2 more lines and you get 40, 2 more lines you get to 50, and 2 more lines and you get to 60. And we know from the data the max number of clusters we have is 51, so going up to 60 is fine. And also the max number of years since 1990 is 10 years because it only goes up to 2000, so that should be sufficient for our data. So the next thing you're going to do to finish making this graph is you're going to give it a title, so we don't have our title here. And we're also going to go ahead and plot the points. I went ahead and wrote an informative title, and yours should also be informative. It shouldn't just be Y versus X or something. You want to say something like active clusters of woodpeckers, like my title here. And then you want to go ahead and plot your data. So because I'm doing this on a screen, it's not the perfect plotting, but it will do for now. So the step 1 is complete. We've made a complete scatter plot, just like the kind that you're going to make. And you're going to make sure to include all these different parts. So again, that's including an informative title, the actual number scaling of your y-axis, and you want to write that it's the y-axis. X-axis, same thing. Number scaling on the x-axis and an informative title, and then an informative title for the full graph. Then you'll draw your points. So step number 2 for the line of best fit is to go ahead and see if you have a correlation. So if you remember, a positive correlation says that with every x value, y value increases. And remember, it's a trend. It doesn't have to be true for every time. So if you look from 1994 to 1995, you have 27 for both of these. That means that it didn't actually increase, but the overall trend is that the values are increasing as we go down. And that's shown on the graph here. So as x is increasing, y is increasing too. So we're going to have a positive slope here, which is a positive correlation. Step number 3 tells us that now we can actually draw a line of best fit. So since we can use a model to show this equation, we can go ahead and actually draw it. So you want to draw it so about half the points are above the line and half the points are below the line. And again, since I'm doing this on a computer, it's not going to be the straightest line, but I'm going to do my best. Okay, so this is a pretty easy one, and the data is actually pretty much follows a line. Sometimes they might be a little bit more clustery or a little bit more, you might have more points above or below, so it might be a little bit harder to find right where that center is, but this one was pretty easy. And if we want to count to just see, we have 1 point below, maybe 2 points below, and then maybe 1, 2, possibly 3 points above. So that's about even above and below. So that's actually a really good line of best fit. So our last step, which is step 4, is to go ahead and make an equation. So if we want to, our ultimate goal here was to write an equation that models the number of active clusters as a function of the number of years since 1990. So we can actually go ahead and do that. And we do that by finding points. I'm actually going to choose one of them that is on the line, which is right here. That's our third point. So this one here, that's 4 years after 1990, and that's 27 clusters for your Y value. And the other point I'm going to choose is just one that appears to be on the graph, which is actually not the point that I circled here, but actually this junction between the X and Y value a little bit lower. So this is going to be at 10 and 50. So our point here is going to be 10 and 50. So at this point you have 2 points, and you should know how to solve this on your own using 2 points and solve for the equation in slope-intercept form. I encourage you to go ahead and solve this on your own, but just so you can check your work, I went ahead and wrote everything out here. So whenever you have 2 points, you need to find the equation of a line. The first thing you do is find your slope, so it's y2 minus y1 over x2 minus x1. I found my slope to be 23 over 6. It's positive, which makes sense because this is a positive correlation. Then we substitute that into y equals mx plus b. So we have y equals m, which is our slope, 23 over 6x, plus b. And then we can take one of our points, it doesn't matter which, I chose the first one, and substitute y, which is 27, in for y here, and 4, which is x, and substitute that in for x here. Once I did that, I found that the 2, you can cancel a 2 out of each one of these. For those of you that might be confused by that, I'm basically just doing the multiplication through here and simplifying. So it ends up being 27 equals 46 thirds plus b. Then I have to subtract 46 thirds from both sides. And in order to do that and make it a little bit easier, I converted this into a mixed number. So I have 27 equals 15 and 1/3 plus b. Subtract 15 and 1/3 from each side to get b alone to solve for my intercept. And you get b equals 11 and 2/3. Then you can substitute both your intercept and your slope back into the equation. So you have y equals 23 over 6x plus 11 and 2/3. You could change this back to to an improper fraction, or you can leave it as it is, or you could even put it as a decimal. I did not put this one as a decimal because it's a number that goes on forever. It would have been 11.6 repeating, and that's messy. So I left it as 11 and 2/3. So this would be your final answer. Hopefully you got something similar. Sometimes when you're doing these, you don't have the cleanest looking numbers or slopes, but it's still an accurate equation. So good luck trying these on your own.